A very good morning to one and all. This is Anusha, lecturer in physics, working in general department at SS Government Polytechnic, Zahirabad. For first year, second sem students, I'm dealing with applied physics with the subject code 18 common 203F. And from our syllabus, we are discussing the fifth chapter, that is electricity and measuring instrument. From this chapter, in today's class, we are going to learn about combination of resistors in series and parallel. We are going to see the resistance of a resistors when they are connected in series and parallel. To understand this, we are using a small PowerPoint presentation. So let us move on to today's class. The main objective of today's class is, on completion of this period, you will be able to understand the resistance in a circuit when resistors are connected in series and parallel. So before moving on to today's class, let us recall what we studied in previous class. We have seen about specific resistance, conductance. So what is today's topic? That is combination of resistors in series connection. Here we can see three resistors R1, R2 and R3 which are connected in series. When we can say that the resistors are connected in series combination, that in a circuit, if the same current flows through all the resistors, then we can say that they are in series connection. So the effective resistance, combining all the three, we can equate it to Rs. Now we are going to find what is the value of Rs. So consider three resistors R1, R2. You can see here R1, R2. I'll show you. We can see here this is R1, this is R2 and this is R3. And combining all these three, we got Rs. So now the current I which flows through R1 and it enters to R2 and finally it reaches R3. In series connection, the current flows only through one path and it will be same. This is very important point to remember, that when resistors are connected in series, the current flows only through one path in the circuit and it will be same when passing through each resistor. So according to Ohm's law, the potential difference across R1 is, as we all know that Ohm's law is V equals to IR. So here across R1 it is V1 equals to IR1. Across R2 it is V2 equals to IR2. And the potential difference across R3 is V3 is equal to IR3. So here we can see that there are changes in voltages and resistance, but I is same. So we can take these three equations as 1, 2 and 3. Now the potential difference V across the series connection, it is V given by V1 plus V2 plus V3. So using equations 1, 2 and 3, we'll substitute what are V1, V2 and V3. So they are I R1 plus I R2 plus I R3. We can take I as common. So we'll get I into R1 plus R2 plus R3. So it is V by I is equals to, we are simplifying it. It is V by I is equal to R1 plus R2 plus R3. So it is equation 4. Now as shown in figure, in case of series connection, the equivalent resistance Rs is given by V by I. So V is nothing but it is the total potential difference in the circuit. That is, by combining V1, V2, V3, we got it as V. So we'll substitute Rs as R1 plus R2 plus R3 using equation 4. Using equation 4, R1 plus R2 plus R3 is equals to V by I. But here V by I is equals to Rs. So Rs is equals to R1 plus R2 plus R3. So what it tells us? It is the effective resistance when resistors are connected in series is given by the sum of all the resistances of resistors. So if we have n number of resistors in series combination, so the equivalent resistance Rs is given by the summation of all the resistances of resistors. So it is the single value of resistance which may replace the number of the resistors in the circuit without changing current and voltage in the network. So that is about the resistors connected in series. Now we'll move on to combination of resistors in parallel connection. Now here you can see R1, R2 and R3 which are connected in parallel connection. So the equivalent of these three is Rp. Now you can see in the diagram, when resistors are connected in parallel combination, the current across them is changing. The path of current flowing in the circuit is changing. So we got I1, I2 and I3 here. Whereas in the previous case, as the path along which the current is flowing in the circuit is same, so we got only one I. Now consider three resistors R1, R2 and R3 which are connected in series. Oh no, it is in parallel. The current I splits into 3 and flows through R1, R2 and R3. Now in parallel connection, the voltage remains the same. Therefore, the total current I equals to I2 plus I3. Now let us see what is I1, I2 and I3. Now what we have seen in parallel connection, voltage remains same. So the potential difference across R1 is V and across R2 is V and across R3 is V. So it is not V1, V2 and V3. It is V only, because when they are connected in parallel connection, the voltage drop across them is same. So it is given by I1 R1 across R1, I2 R2 is the potential difference across R2 and I3 R3 is potential difference across R3. So V I1 R1, I2 R2, I3 R3. Using this relation, I1 is given by V by R1, I2 is given by V by R2 and I3 is given by V by R3. So we have taken them as equation 2, 3 and 4. Now substituting 2, 3 and 4 in equation 1. So we have seen that I equals to I1 plus I2 plus I3. So that is V by R1 plus V by R2 plus V by R3. Now in this parallel combination, the equivalent resistance Rp is given by V by Rp is equals to I. Now substitute this in equation 5, we'll get V by Rp is equals to V by R1 plus V by R2 plus V by R3. We can take V common on right hand side, and when we simplify it, we'll get 1 by Rp is equals to 1 by R2 plus 1 by R2 R1 plus 1 by R2 plus 1 by R3. If there are n number of resistors in parallel, so it is so on up to 1 by Rn. So in a parallel connection, the total resistance of a circuit is determined by adding the reciprocal of the resistance of each individual resistance, and it is always less than the smallest resistor present in the circuit. As it is reciprocal, we'll get the value of it as very less. Now let us summarize it. We have discussed the following. We have seen the combination of resistors in series connection and parallel connection. So let us solve some questions here. Calculate the total resistance between the points A and B. You can see when I is traveling from A to B, at the middle of its, or else on the way, you can see 1 ohm and 2 ohm. Here the path of current is changing. So these two are connected in parallel. So first we'll find the resistance across 1 and 2, and then 4 ohm, 3 ohm and the result of 1 ohm and 2 ohm. All these three will be in series. It is preferable to connect bulbs in series or in parallel. So it is preferable to connect bulbs in parallel combination. Calculate the equivalent resistance between A and B. So you can see 5 and 15 are in series, 10 and 20 are in series, or else we can say 5 and 10 are in parallel, 15 and 20 are in parallel. So using this, we can find the equivalent resistance between A and B. Now in a which circuit the total resistance is greater than the largest resistance in the circuit? So it is in series combination. The batteries are generally connected in series so that we can increase the resistance value. If two bulbs are connected in parallel and one bulb blows out, what happens to the other bulb? So as they are connected in parallel, the path of current across these two bulbs is different. So if one bulb blows out, the other bulb continues to glow with the same brightness. So here are some frequently asked questions. Derive expression for effective resistance in series combination of resistors. Derive expression for effective resistance in parallel combination of resistors. So with this we are concluding. Thank you so much for attending the class. To understand the concept of resistors when they are connected in series and parallel, let us go through a small video which is explaining us how current flows when resistors are connected in series and parallel in a circuit. Watch clearly, listen carefully, and try to understand when resistors are connected in series and parallel combination in a circuit.
Zamat, Electronics for Beginners. Today we are going to learn about resistors. We know electrical resistance is opposition to the flow of current in an electric circuit. The resistor's resistance limits the flow of electrons through a circuit. This is a conductor. Assume it has zero resistance. If we apply a voltage difference, then the electrons start to move through the conductor. A moving electron flow is a negative current flow. We can measure the amount of current using an ammeter. Here we have very high current because the conductor has no resistance to slow down the electrons. They move at full speed. Let's consider another conductor, but it has a resistor. Apply the same amount of voltage like the first one. Electrons start to flow, but electrons have no other option. They have to go through the resistor. Let's look at the ammeter reading. It's less than the first reading. Resistor limits the electron flow. Let's try another conductor that has two resistors in series. Current flow has to pass both obstacles. So the ammeter reading is lesser than earlier. Likewise, we can add more resistors in series and increase the resistance. This is the symbol of resistor. The total resistance is now R1. If we add another resistor that has R2 resistance, the total resistance becomes R1 plus R2. Let's add another R3 resistor in series. The total resistance increases furthermore. Now the total resistance is R1 plus R2 plus R3. So in general, the total resistance of the series resistors are equal to the sum of individual resistance. Let's go back again. We know series resistors reduce the current. Assume this resistor only allows I1 current to go through it. Now the ammeter reading is I1. What happens if we connect two resistors that has same resistance in parallel and apply the same voltage across those? Each resistor allows I1 current to go through it. Now the ammeter reading is equal to I1 plus I1, that is 2I1. You see, the current has increased. That means the total resistance has decreased. Using parallel resistors, we can reduce the resistance. Look at this circuit. V, R and I are the voltage, resistance and current between points A and B. If we add an R1 resistor between point A and B, it will pass I1 current through it. Current has no other way to go from A to B. So, the total current is equal to I1. Using the Ohm's law, we can replace the current by using voltage and resistance. Now, we can remove the term voltage from both sides. We are getting an equation like this. Right. Let's add another resistor parallel to the R1, like this. This new R2 resistance allows I2 current to pass it. Now the current has two ways to go from A to B. So the total current is equal to the sum of these two currents, I1 plus I2. We can replace the I using Ohm's law and simplify the equation like this. We can keep adding resistors and continue this for more parallel resistors. For 3 parallel resistors, we can build an equation like this. In a parallel resistor circuit, the inverse of the total resistance is equal to the sum of inverse of each individual resistor.
Hope you understood what happens when resistors are connected in series and parallel in a circuit. So when they are connected in series, the resistance, the equivalent, the total resistance in the circuit increases. So when resistance increases, the flow of current will be less. And when they are connected in parallel, the equivalent resistance in the circuit is decreased. So when resistance is decreased, the flow of current will be increased. So this is the conclusion for our topic. When resistors are connected in series and parallel combination in a circuit.